It's amazing when you think about it, right? Even in math, something we think of as super precise, there are these weird kind of
Oh,
limits.
yeah, totally.
Like if you take a simple square, its sides and its diagonal, they're what Euclid called incommensurable.
Yeah.
No shared unit of measurement. Makes you wonder if that same kind of fundamental gap pops up in science too, right? A world we usually think of as rational and all.
It does make you wonder. And that's exactly what we're going to dive into today, this whole idea of incommensurability between the scientific theories. It's a concept that caused quite a stir in the philosophy of science, especially back in 1962 when Thomas Kuhn and Paul Feyerabend really brought it to the forefront.
1962, huh?
Yeah.
The year this idea really hit the scene. So these guys, Kuhn and Feyerabend, they were basically saying that when science goes through these big shifts, these revolutions, it's not just a matter of adding new facts to what we already know. It's more like the old and the new ways of doing science become, well, kind of incommensurable.
Right. And that was a pretty radical idea for a lot of people back then, especially for those who saw science as this steady march towards the truth.
Yeah, like science is always building on what came before, always getting closer and closer to the ultimate answer.
Exactly. And Kuhn and Feyerabend were challenging that view. They suggested that these revolutionary transitions in science are so profound, so fundamental, that you can't really compare the theories on either side of the divide using any kind of shared standard or common measure. Which naturally led to some big questions about how rational science really is and what progress even means in science. Pretty philosophical stuff, huh?
And for our listeners out there who love to think about these big questions, this isn't just some dusty old debate in the philosophy of science. This idea of incommensurability really gets at the heart of how we know anything at all. How does knowledge actually change and evolve? How can you even relate to totally different systems of thought when their basic assumptions are so radically different? And if the very criteria we use to judge progress are always changing too, then what does progress even mean?
You're hitting on some really key points. These are questions that resonate not just within science, but in any field of knowledge where you have these huge shifts in perspective.
It's like you're trying to translate between two languages that have completely different ways of seeing the world.
Exactly. And in this deep dive, we're going to really unpack this concept of incommensurability. We'll start with Kuhn and his ideas about paradigms and paradigm shifts. Then we'll move on to Feyerabend, who brought in this notion of meaning variance and something he called deductive disjointedness. We'll trace how their ideas developed, look at who influenced their thinking, and then finally compare and contrast their views.
Sounds like a plan. All
Yeah.
right, so let's start with Thomas Kuhn. His book, The Structure of Scientific Revolutions, really shook things up, right? So what was his take on this whole incommensurability thing?
Yeah, in structure, Kuhn made this really compelling case that when you have different paradigms competing with each other, these big overarching frameworks that sort of define what questions are worth asking and what methods are okay to use within a field, well, the people working within those different paradigms often end up talking past each other.
So it's not just that they disagree on the answers, they might not even agree on what the right questions are.
That's exactly it. And Kuhn argued that the traditions of science before and after a major revolution are incommensurable.
Like oil and water, they just don't mix.
Exactly. He used some great historical examples, like the shift from Newtonian physics to the older Aristotelian view, or in chemistry, how Lavoisier's oxygen theory replaced Priestley's idea of phlogiston. And the heart of this incommensurability for Kuhn was the lack of a common measure. You have these rival paradigms with their own unique concepts, their own ways of doing things, their own problems they're trying to solve. It's like they're speaking different languages, and that makes it really tough to compare them directly.
And this idea was a direct challenge to that classic picture of science as this slow, steady accumulation of knowledge, right?
Yeah, the view that science is always getting closer and closer to the truth. Kuhn pushed back against that pretty hard. He argued that you can't assume there's this unchanging, neutral set of rules that scientists have always used to decide which theories are better.
Because the rules of the game change too, right? With each revolution, there's a new set of standards.
Right. And Kuhn even compared scientific change to evolution in biology. He said science doesn't move directly towards some fixed goal, but rather away from problems and anomalies, things the current theories can't explain.
It's like science is constantly trying to escape its own limitations.
That's a great way to put it. Now, Kuhn did refine his ideas about incommensurability later on. His initial presentation and structure was open to some interpretations that he didn't quite intend.
Like some people thought he was saying that scientific change is just totally random or irrational.
Yeah, there was some pushback about that. And he wanted to make it clear that incommensurability doesn't mean you can't compare theories at all. It also doesn't mean that science is just this irrational free-for-all.
So what did he emphasize in his later work?
He started to focus more on what he called conceptual incompatibility. He looked at how different theories classify the world, like what fundamental kinds of things they say exist and how they relate to each other.
So like in biology, different theories might categorize species in different ways.
Yeah.
Or in chemistry, how they define elements.
Exactly. And this led him to challenge one of the big ideas of logical positivism. The belief that you could always translate the claims of different scientific theories into some kind of neutral observation language. This neutral language would be the common ground for objectively comparing the theories. But Kuhn argued that this kind of translation isn't always possible.
Interesting. So the very language we use to describe the world is already shaped by the theories we hold.
Yes, and later on in the 1990s, he even talked about incommensurability in terms of ineffability. He suggested that certain statements and concepts only make sense after a specific theory has come along. If you try to express those ideas using the vocabulary of an older theory, they would just sound nonsensical.
It's like the new theory opens up a whole new way of thinking and talking about the world.
That's a great way to put it. And all of this led Kuhn to his idea of taxonomic incommensurability, because new theories often classify things in ways that clash with the classifications of older theories. You get this kind of translation breakdown between them. It's not just that they use different words, it's that they divide up reality in different ways. And Kuhn was careful to distinguish this taxonomic incommensurability, which is about concepts, from methodological incommensurability.
Which is about the values scientists use to compare theories, right?
Right. Right. And this methodological incommensurability acknowledges that scientists might value different things, like a theory's scope, its simplicity, its ability to predict new things, or how accurate it is. So you can have rational disagreement about which theory is better based on how you weigh those values.
Makes sense. So what was the aha moment for Kuhn? What led him to this idea of incommensurability in the first place?
He actually described this kind of gestalt switch experience he had as a grad student when he was wrestling with Aristotle's physics. He kept coming across passages that seemed totally nonsensical, and he couldn't figure out how someone as brilliant as Aristotle could have written them. Then it suddenly hit him. He'd been reading Aristotle through modern lenses, trying to impose modern meanings onto these ancient texts.
Like he was trying to fit a square peg into a round hole.
Yeah, exactly. He realized that to really understand Aristotle, he had to forget about his modern scientific assumptions and really try to get inside Aristotle's head, see the world through his eyes.
That's fascinating. So he had to learn a whole new way of thinking to grasp what Aristotle was saying.
He really did. And that's when he shifted his focus from physics to the history and philosophy of science. Now, it wasn't just this personal experience that influenced him. He was also heavily influenced by a guy named Ludwig Fleck.
Never heard of him. Who was he?
He was a Polish bacteriologist who back in the 1930s was already developing what we now call the sociology of scientific knowledge. And Kuhn was especially struck by Fleck's 1935 book. It had this kind of paradoxical title, Genesis and Development of a Scientific Fact.
So this book was about how scientific facts are actually socially constructed.
Yeah, it was pretty groundbreaking for its time. And guess what? Fleck himself used the term incommensurable, but in German, of course. He used it to describe different thought styles within science, like how medical thinking is different from scientific thinking in general.
So Fleck was already onto this idea of incommensurability before Kuhn.
Yeah, in a way he was. But Fleck focused more on how concepts develop and change meaning within entire scientific communities, while Kuhn initially focused more on the individual scientist's experience.
So kind of a bottom-up versus a top-down perspective.
You could say that. And Fleck also saw meaning change as more gradual and continuous, whereas Kuhn made this sharp distinction between periods of normal science, where meanings are relatively stable, and those revolutionary periods where everything gets turned upside down.
But there were definitely overlaps in their thinking, right?
Oh, absolutely. Fleck also talked about how scientific revolutions involve a whole bunch of interconnected changes, like what problems scientists consider important, how they go about solving those problems, the basic concepts they use, and even how they perceive the world itself. And he also argued that scientific progress isn't necessarily about getting closer to some ultimate truth, because new thought styles bring new problems to the table, and sometimes we just abandon old forms of knowledge altogether.
So it's not always a forward march. Sometimes it's a sideways step or even a step back.
Exactly. And just like Kuhn, Fleck argued that the meaning of scientific terms comes from how they're used within a specific theory, and those meanings change as theories evolve. He even used the same example as Kuhn about the changing meaning of chemical elements and compounds. He really stressed that observation is always theory-laden.
Meaning, we don't just see the world as it is, but through the lens of our
Yep.
theories.
Exactly. He even talked about Gestalt switches to show how our thought style shapes not only how we understand concepts, but also how we literally see the things we're studying. And he also anticipated Kuhn's later focus on the problems of translating between theories because of these differences in thought styles. So you can see how Fleck was already grappling with a lot of these really complex issues. Now, besides Fleck, were there any other influences on Kuhn's thinking?
You mentioned Gestalt psychology earlier.
Right, that was a big one, especially the work of Wolfgang Kohler.
Refresh my memory. What was Gestalt psychology all about?
It emphasized that we perceive things as wholes, as Gestalten, before we break them down into their parts.
So we see the forest before we see the individual trees.
Yeah, that's a good analogy. And Kohler himself, when he was exploring the relationship between psychology and physics, even suggested that if we can't seem to connect those two disciplines, it might be because their basic categories are incommensurable, which is a pretty radical thought.
It is. It makes you wonder if there are fundamental limits to how much different fields of knowledge can ever truly understand each other.
Exactly. And Kuhn also found inspiration in a surprising place: art. In one of his early manuscripts, before Structure was published, he actually used the idea of incommensurability to contrast the way progress happens in art versus science.
Because we usually think of science as cumulative, building on past knowledge, but art doesn't really work that way, right?
Yeah, that's the traditional view. But Kuhn wanted to challenge that, to show that scientific progress can be a lot more like art than we might think. He said that when a new scientific theory comes along, it often redefines the whole field. Old problems become irrelevant, new ones emerge, and the standards for what counts as a good explanation change too.
It's like a whole new game with different rules.
Exactly. And he argued that this new science that emerges from a revolution isn't just an addition to what came before, it's something fundamentally different, even incommensurable with the old science.
So from Aristotle to Fleck, to Gestalt psychology and even art, Kuhn drew from a pretty wide range of sources to develop his ideas. Now, how did his thinking evolve after Structure came out?
He kept working on these ideas throughout his career, and around 1987, he felt like he'd made some significant breakthroughs. We already touched on this, but his initial view of incommensurability, which was pretty broad, became more clearly divided into taxonomic incommensurability and methodological incommensurability.
So taxonomy is about concepts and methodological is about values, right?
Right. And this distinction gives us a more nuanced way to understand how theories can be incommensurable.
All right, so let's dig into this taxonomic incommensurability a bit more. What's the core idea here?
It revolves around what Kuhn called the no overlap principle. This principle says that when you're classifying things within a theory, like, dog, cat, gold, silver, these kinds of terms that are important for scientific laws and theories, well, these kind terms can't overlap unless they're related, like a species and its genus. So something can't be both a dog and a cat at the same time. Kuhn argued that scientific revolutions actually disrupt this principle.
So they mess up our neat categories.
They do. Theories before and after a revolution classify things in ways that are fundamentally different, even mutually exclusive. So what's one kind of thing according to one theory just can't fit into the categories of the other theory, and this creates all sorts of problems for comparing them.
Can you give an example of this no overlap principle being violated during a scientific revolution?
Sure. A classic example is the shift from Ptolemy's geocentric model of the universe to Copernicus's heliocentric model.
So the Earth-centered view versus the sun-centered view.
Exactly. In Ptolemy's model, the sun was classified as a planet orbiting the Earth. But in Copernicus's model, the sun is a star, and the Earth is now a planet orbiting the sun. So the same object, the sun, gets classified in two completely different ways. And that means it's understood to be governed by totally different rules. Like, the statement, planets orbit the sun, makes perfect sense in the Copernican system, but it's actually incoherent in the Ptolemaic system.
Because in that system, the sun is a planet, and planets, by definition, orbit the Earth.
Right. It's not just a disagreement about which object is orbiting which. It's a fundamental difference in how they categorize the whole cosmos.
Wow, that's a really clear example of how these shifts in classification can lead to incommensurability. So it's not just about using different words, it's about having different ways of carving up reality itself.
Precisely. And Kuhn even drew an analogy with evolution here. He said that scientific revolutions can be like speciation in biology, where one species splits into two. He suggested that revolutions can cause a scientific discipline to branch out into subdisciplines that have their own incompatible categories and terms.
So, like, different scientific dialects?
Yeah, you could think of it that way. And he even compared these specialized vocabularies, these lexical taxonomies, as he called them, to Kant's a priori categories.
But in a kind of relativistic sense, right? Not fixed and universal like Kant thought.
Exactly. Each lexicon creates its own form of life, so to speak, with its own rules for what's true and false. And because there's no neutral way to compare these different lexical structures, Kuhn rejected the idea that science is gradually zeroing in on some ultimate truth. He argued that we choose our scientific vocabulary based on how useful and coherent it is for the community that's using it.
So it's more about pragmatism than about finding some absolute truth.
That's right. And this skepticism about ultimate truth also extended to the idea of a theory's ontology, its picture of what really exists.
So Kuhn didn't believe that a theory could perfectly mirror reality.
He really didn't. He thought the idea of a perfect match between a theory and the world was kind of an illusion. He also argued that our vocabulary not only allows us to say certain things, but also limits what we can even express. So some statements that make perfect sense in one theory might be ineffable in another. You just can't say them because the concepts aren't there. And this even changed how he thought about understanding the history of science. He started to see it more as learning a new language, becoming bilingual, so to speak, than as translating between theories.
Because a true translation might not even be possible.
Yeah, that's right. And this has some pretty big implications for how we understand the relationship between past and present science. All right, I think we've covered Kuhn pretty thoroughly. What about Feyerabend? How did he approach this whole incommensurability thing?
Yeah, let's jump into Feyerabend's world.
Okay, so Feyerabend, in his 1962 essay, Explanation, Reduction, and Empiricism, he really zeroed in on incommensurability as this very specific kind of clash between concepts, a clash that leads to completely different interpretations of reality. For him, two theories were incommensurable if the way concepts were formed in one theory actually made it impossible to form the basic concepts of the other theory.
So it's like the two theories are built on foundations that just can't coexist.
Yeah, like they're trying to build houses on completely different types of ground. He even said that a new incommensurable theory would basically imply that the things the old theory was talking about didn't even really exist in the way the old theory described them.
That's a pretty radical claim. It's like the new theory wipes out the reality of the old one.
It's strong stuff, for sure. And Feyerabend saw this incompatibility on two levels. First, on the level of concepts, because of what he called meaning variance, the terms just don't mean the same thing. And second, on the level of ontology, the theories have fundamentally different views of what reality is made of. He argued that the meaning of a scientific term comes from the whole network of theoretical principles that surround it. And these principles, in turn, lead to totally different explanations of the world.
So the meaning of a word is like a spider web connected to all these other ideas.
That's a great way to visualize it. And this has some big implications for how we understand language itself, especially in science.
Definitely. So for Feyerabend, what was the main consequence of this incommensurability? How did it affect how we compare scientific theories?
Well, he said that theories that are incommensurable are also deductively disjoint. This means that you can't use the logic of one theory to understand or explain the other. Because their core concepts are so different, you can't define the terms of one theory using the terms of the other. And any predictions you make from one theory won't logically contradict or support the predictions of the other.
So it's like they're speaking different logical languages.
Yeah, you could say that. He even went so far as to say that incommensurability is deductive disjointedness, and that's all it is. This means you can't logically derive one theory from the other, and you can't use the success of one theory to prove or disprove the other. And this creates a problem for those classic ideas about how we test scientific theories.
Right, because if they're deductively disjoint, how can you even use evidence to compare them?
That's the challenge. And Feyerabend tackled it head on. He actually came up with an alternative model of scientific testing that could work even between theories that are incommensurable. He didn't believe that incommensurability made theories untestable. He drew inspiration from David Bohm and used Einstein's prediction of Brownian motion as a prime example. See, Einstein's work led to this amazing test between kinetic theory and classical thermodynamics.
I mean, these two theories were incommensurable.
That's right. but the kinetic theory was able to predict this weird random movement of particles called Brownian motion, something classical thermodynamics just couldn't explain. And for Feyerabend, this was a case of novel corroboration. The kinetic theory's success in explaining something brand new gave it a huge boost, even though it couldn't be logically derived from or directly compared to classical thermodynamics. So his view was that having these rival theories that are incommensurable actually makes science more testable.
It's like they force each other to up their game.
That's a great way to put it. And he argued that classical thermodynamics only really faced a serious challenge because the kinetic theory came along with its radically different way of seeing things. He also developed this idea of a contrastive account of empirical content, where the meaning and value of the evidence are determined by the contrast between the theories, by what each theory can and cannot explain. And for Feyerabend, scientific progress wasn't about slowly refining our theories or absorbing old theories into new ones. It was about outright rejection and replacement, leading to this ever-expanding pool of alternative theories that push each other further.
So a kind of survival of the fittest for scientific ideas.
That's the idea. So how did Feyerabend arrive at these radical views? It turns out he'd been thinking about conceptual change for a long time. Even before that 1962 essay, he was already discussing these ideas with a group of philosophers in Vienna called the Kraft Circle. This was back in the late 40s and early 50s, when he was working on his PhD. He even presented his ideas to Karl Popper's seminar in London and to Ludwig Wittgenstein's group in Cambridge. Early on in his thesis, he argued that the way we interpret observations depends on the theories we're using, and that interpretation changes when our theories change. He used temperature as an example, saying its meaning should be based on statistical thermodynamics, not just on how it feels to us or how we talk about it in everyday life. And this was a direct challenge to the logical positivists who thought you could ground scientific language in pure experience. Feyerabend was saying, no, theories actually shape how we experience the world.
That's a pretty big shift in perspective.
It is. Now, his relationship with Popper, his old mentor, well, that was complicated, to say the least.
Yeah, I've heard they had a bit of a falling out.
They did. Popper was Feyerabend's supervisor initially, but they ended up disagreeing pretty strongly about how science works. Some people saw Feyerabend's ideas about incommensurability as just an extension of Popper's views on how theories get replaced. But Feyerabend was actually criticizing Popper, saying that Popper's ideas couldn't handle incommensurable theories and that this was holding science back.
So Feyerabend was even more radical than Popper.
In a lot of ways, yeah. Now, besides Popper, were there other key figures who influenced Feyerabend?
Definitely. One was Pierre Duhem, a French physicist and philosopher of science. Feyerabend was a big fan of Duhem's book, The Aim and Structure of Physical Theory. Duhem argued that logic alone can't settle scientific debates, and he pointed out how tough it is for historians to understand old scientific ideas because the meanings of terms change so much over time. He also highlighted the communication problems that arise between scientists who are working within different theories, and this all fits very nicely with Feyerabend's own emphasis on incommensurability. Duhem also argued that even experimental results are theory-laden. They're not just pure observations. They're shaped by the theoretical assumptions of the scientists who are conducting the experiments. So Duhem was already laying the groundwork for a lot of the ideas that Feyerabend would later develop. It's amazing how these ideas build on each other over time.
It really is. Now, Niels Bohr also had a big influence on Feyerabend. They had a lot of discussions about things like irrational numbers and the development of quantum mechanics. But Feyerabend was critical of Bohr's complementarity principle, which tried to use classical concepts to describe quantum phenomena.
So Feyerabend thought Bohr was being too conservative.
Yeah, he thought Bohr was clinging to old ways of thinking. He argued that classical physics could be completely replaced by a theory that's totally incommensurable with it, and he used the shift from Newtonian physics to Einstein's relativity as an example. He said these two theories have completely different fundamental concepts with no logical connection between them.
So for Feyerabend, a scientific revolution could be a truly radical break, a complete paradigm shift.
Exactly. And what about Einstein? Did he influence Feyerabend?
That's a good question.
Right. He did. Einstein actually used the term incommensurable himself, but he used it in a slightly different way. He talked about the need to weigh incommensurable qualities when judging different theories, things like how natural or logically simple a theory is. And there's strong evidence that Feyerabend was directly inspired by this. They both drew a distinction between universal theories and more specific ones, and they both focused on how incommensurability relates to basic theoretical concepts. It's also interesting that Einstein saw theoretical categories as being like free conventions, almost like they're chosen rather than discovered, and both Kuhn and Feyerabend adopted similar views.
So they all agreed that our theoretical frameworks aren't just given to us by the world, they're also shaped by our choices and decisions.
That's right. And Feyerabend even explicitly said that his ideas weren't totally new. He argued that physicists like Mach, Boltzmann, Einstein, and Bohr had already been thinking along these lines. So for him, incommensurability wasn't just some abstract philosophical idea, it was something that was already present within science itself.
So he saw himself as part of a larger conversation, not just some outsider critiquing science from afar.
That's a good way to put it. And later on, he actually broadened the idea of incommensurability even further. He started applying it to things like worldviews, historical periods, different cultures, even different ways of perceiving the world. For him, anytime you have a clash of fundamental principles, you might have incommensurability.
So it becomes this really broad concept applicable to all sorts of domains.
Exactly. Now, how do Kuhn and Feyerabend's views on incommensurability compare? Initially, Feyerabend had a more precise and narrowly focused definition. He was primarily interested in the conceptual structure of those big universal scientific theories and what those theories say about the nature of reality. Kuhn, in structure, took a broader view. He included things like methods, observations, concepts, and even what he called world change, though he admitted later that he couldn't fully explain that last one.
So Feyerabend was more focused on the building blocks, while Kuhn was looking at the whole architecture.
That's a good analogy. And it's interesting that their paths kind of converged after 1962. Kuhn narrowed his focus down to concepts, especially with his taxonomic incommensurability, which was closer to Feyerabend's starting point. Meanwhile, Feyerabend started to emphasize things like perceptual change, the role of problems in science, and even those values that scientists use to judge theories. So he was moving towards some of the broader concerns that Kuhn initially raised.
So their ideas kind of danced around each other, influencing and shaping each other over time.
You could say that. They also disagreed on which theories were actually incommensurable. Feyerabend mainly stuck with those big universal theories that claim to describe reality as a whole because he was interested in their ontological implications and how we test them. Kuhn applied the concept more broadly, including to smaller scale theories and more localized changes in concepts. A good example is the Ptolemaic versus Copernican shift. Kuhn saw that as a classic case of incommensurability, but Feyerabend wasn't so sure because planetary theory isn't really universal in scope.
It doesn't encompass the whole of reality.
That's right. And Kuhn later emphasized what he called local incommensurability. He thought that conceptual change might sometimes be limited to a small cluster of related ideas, which means you could still compare some of the empirical predictions of the theories. Like in the geocentric and heliocentric models, you could still compare their predictions about where the planets would appear in the sky.
Even though their fundamental concepts were different.
Yeah, he thought so. But Feyerabend stuck with a more global view of incommensurability. For him, when meanings change, they affect pretty much everything the theories say, which means you can't really compare their predictions in any meaningful way.
So for Feyerabend, the incommensurability was more pervasive, more deeply rooted.
That's right. Now, there's this question that comes up a lot when people talk about incommensurability. Does it mean that you can't compare theories at all?
Like they're just totally isolated, each in its own little bubble.
That's the worry. But both Kuhn and Feyerabend said, no, that's not what incommensurability means. They both argued that comparing theories is just more complicated than some philosophers thought. Kuhn said that it's not a simple step-by-step process. You don't need a neutral language to do it. It involves weighing different values, and that can lead to reasonable disagreement between scientists. He even said that recognizing incommensurability is crucial for being intellectually honest, and it helps us avoid those extreme relativist views that say anything goes in science.
So it's a safeguard against taking things too far.
Yeah, that was part of his point. And Feyerabend went even further. He said that developing rival theories that are incommensurable is actually the best way to put our existing theories to the test. Because some of the most important challenges to a theory only come from perspectives that are radically different from it.
It's like you need an outsider's perspective to really see the flaws in your own thinking.
That's a good way to think about it. And while Feyerabend criticized Popper's strict idea of falsification, proving a theory wrong definitively, he didn't think that meant theories were untestable. His Brownian motion example was meant to show that you can still compare theories empirically, even if there's no neutral observation language. And he even acknowledged what we now call methodological incommensurability, the idea that different theories might value different things.
So even though there's incommensurability, you can still have reasoned debate and comparison between theories.
That was their view. And finally, I want to highlight one big thing that Kuhn and Feyerabend agreed on. They both rejected the idea that science is getting closer and closer to some ultimate truth. They saw scientific revolutions as these big sweeping changes where whole conceptual frameworks, whole ways of seeing the world get replaced. It's not just about adding new pieces to the puzzle, it's about changing the puzzle itself.
So they were both skeptical of that traditional picture of scientific progress as a steady march towards the truth.
Absolutely. All right, I think we've really gone deep on this topic of incommensurability. Any final thoughts for our listeners?
This has been a really thought-provoking deep dive. It really makes you think about how we know anything at all, especially in science. If Kuhn and Feyerabend are right, then science isn't always this straightforward linear process. It's full of these twists and turns, these radical shifts in perspective, where the very ground of knowledge can change beneath our feet. This has implications not just for science, but for any field where people are trying to understand the world. And here's a question for you, our listeners, to ponder. If our thinking is so deeply shaped by our theories, our conceptual frameworks, can we ever really understand a view that's fundamentally different from our own? Are we always talking past each other to some extent? And could accepting the possibility of incommensurability actually help us be more open-minded, more tolerant of different perspectives? Because maybe, just maybe, there are multiple valid ways of understanding the world, even if they're incommensurable with each other.
That's a great question to end on. Food for thought, for sure.
Yeah, it really makes you think. Thanks for joining us for another deep dive.
You got it.